Welcome to the seventh module of the Securian Bootcamp. This module is about Audit Findings 101, where we will review 101 findings from public audit reports of leading audit firms to get a sense for the kinds of issues reported during audits and their suggested fixes or recommendations. These 101 findings range from medium severity to high-end critical, and so are of the highest concern that could have led to loss of funds or significantly affected execution if they had not been detected and fixed during audits. To help level set expectations, we will only be able to touch upon key aspects of these findings in this video presentation and hope to discuss any particular ones of interest in other forums of the bootcamp. The reason is that these findings require a lot of context from the deepest details of the protocol implementations, which we will certainly not have the time to do so for all the 101 findings. This will need to be done by the bootcamp participants in their own time, by reviewing the audit reports and their corresponding protocol code bases to whatever extent possible in the available time. So I would strongly encourage everyone to do so and to at least read the audit reports covered here, if not the actual code bases of the audited projects themselves. For each finding, we will review the vulnerability category, severity, its finding summary, and the proposed recommendation, while tying some of these aspects to our learnings from the earlier modules. So with that, let's get started. The first one is a finding from consensus diligence audit of Aave V2 protocol. It was a medium severity finding in the error handling category. Specifically, this was about unhandled return values of transfer and transfer from functions on ERC20 tokens. Recall that these ERC20 functions may revert, return a boolean, or not return any value at all. And therefore, any code using such functions on external ERC20 tokens should anticipate all such scenarios, because ERC20 implementations are not always consistent and adhere to the specification. And as discussed in number 149 of Solidity 201 module, it is safer to instead use OpenZeppelin's safe ERC20 wrapper functions in such cases. The specific recommendation made here by the audit team was to check the return value and revert on 0 or false, or use OpenZeppelin's safe ERC20 wrapper functions. This finding was in consensus diligence audit of the DeFi Saver protocol. It was a critical vulnerability of the reentrancy type, which allowed for a random task execution in the context of the protocol. Specifically, in a scenario where a user took a flash loan, one of the functions gave the flash loan wrapper contract permission to execute functions on behalf of the user's DS proxy. And this permission was revoked only after the entire SP execution finished, which meant that in a case that any of the external calls along the SP execution was malicious, it could perform a reentrancy attack by injecting any task of choice leading to users' funds being transferred out or draining approved tokens. This vulnerability was due to potential reentrancies from malicious external calls, and therefore the recommendation was to add a reentrancy guard such as the one from OpenZeppelin, where the non-reentrant modifiers are used on functions that may be vulnerable to reentrancies. We have discussed these aspects in number 157 of Solidity 201 module and number 13 of Security Pitfalls and Best Practices 101 module. Number 3 is again another finding from consensus diligence audit of the DeFi Saver protocol. This was a major severity finding in the input validation category, where tokens with more than 18 decimal points could have caused issues. The code assumed that the maximum number of decimals for each token is 18. However, although this is uncommon, but it is possible to have tokens with more than 18 decimals. For example, YAM version v2 has 24 decimals, and interacting with such tokens could have resulted in broken code flow and unpredictable outcomes. The specific recommendation was to make sure that the code won't fail in case the token's decimals is more than 18, and was fixed by using safemap sub function to revert on tokens that have greater than 18 decimals. We have discussed this aspect of ERC20 decimals in number 104, 159 and 170 of Security Pitfalls and Best Practices 201 module. Number 4 is another finding from consensus diligence audit of the DeFi Saver protocol. This was a major severity in the error handling category, where error codes of a few compound protocols functions called by these contracts were not checked. Some of compound protocols functions return an error code instead of reverting in case of failure, but DeFi Saver contracts never checked for error codes returned from such compound functions, causing them to not react to exceptional conditions in such function calls by reverting or other means as necessary. The specific recommendation was for the caller contract to revert in case the error code returned was not 0, indicating a failure, and this was fixed accordingly. We have discussed this aspect of checking for function return values in number 142 and 175 of Security Pitfalls and Best Practices 201 module. Number 5 is yet another finding from consensus diligence audit of DeFi Saver protocol. This was a medium severity in our ordering category, and this vulnerability was due to the use of a reversed order of parameters in the allowance function call, where the parameters that were used for the allowance function call were not in the same order as what was later used in the call to safe transfer from. The recommendation was to reverse the order of parameters in the allowance function call to fit the order in the safe transfer from function call, and was fixed by swapping the order of parameters. We have discussed the concepts of ERC20 token allowance and safe ERC20 wrappers in number 148 and 149 of Solidity 201 module, and this exact specific aspect of checking for ordering issues of function arguments in number 139 and other security impacts of broader ordering issues in number 145 and 178 of Security Pitfalls and Best Practices 201 module. Number 6 is a finding from consensus diligence audit of the DAO 5 protocol, where it was a critical severity finding in the input validation category. The finding here was that token approvals can be stolen in the add liquidity function of the protocol, where the function created the desired pair contract if it did not already exist, then transferred tokens into the pair. However, there was no validation of the address to transfer tokens from, and so an attacker could have passed in any address with non-zero token approvals to the DAO5 V1 router. This could have been used to add liquidity to a pair contract for which the attacker was the pair owner, allowing the stolen funds to be retrieved using the withdraw function. The recommendation was to transfer tokens from message sender instead of LP sender. We have discussed the importance of access control checks on correct addresses in number 148, 149, 160, 172, 180, 181 and 183 of Security Pitfalls and Best Practices 201 module, and also the importance of input validation specifically on function parameters, tokens, and addresses in 138 and 159 of Security Pitfalls and Best Practices 201 module. Number 7 is another finding from consensus diligence audit of the DAO 5 protocol, where it was a major severity finding in the error handling category. The error was that swap exact tokens for ETH checked the wrong return value. Instead of checking that the amount of tokens received from a swap was greater than the minimum amount expected from the swap, it calculated the difference between the initial receiver's balance and the balance of the router. The recommendation was to check the intended values. We've discussed this aspect of correctly checking function return values in number 142 and 175 of Security Pitfalls and Best Practices 201 module. Number 8 is another finding from consensus diligence audit of the DAO 5 protocol, where it was a medium severity finding in the denial of service category. In this case, the DAO 5 even pair deposit function accepted deposits of zero amounts, blocking the pool thereafter. This was because the function allowed only a single deposit to be made and no liquidity could ever be added to a pool after the deposit variable was set to true. However, the deposit function did not check for a non-zero deposit amount and so therefore allowed a malicious user that did not hold any tokens to lock the pool by calling deposit without first transferring any funds to the pool. The recommendation was to require a minimum deposit amount with non-zero checks. We have discussed denial of service in number 176 of Security Pitfalls and Best Practices 201 module, and also the importance of input validation, specifically on function parameters in 138 and number 146 of Security Pitfalls and Best Practices 201 module. Number 9 is a finding from consensus diligence audit of the FATE protocol, where it was a critical severity finding in the application logic, where the Genesis group commit function overrode previously committed values. The amount stored in the recipient's committed FGen balance overrode any previously committed value, including allowing anyone to commit an amount of zero to any account, deleting their commitment entirely. The recommendation was to ensure that the committed amount is added to the existing commitment instead of overriding it. This finding is related to the numerical and accounting issues we discussed in number 170 and 171 of Security Pitfalls and Best Practices 201 module, and also the general challenges of detecting application-specific business logic issues in number 191 of that module. Number 10 is another finding from consensus diligence audit of the FATE protocol, where it was a critical severity finding related to the timing category. Here, purchasing and committing was still possible after launch, which meant that even after the Genesis group launch had successfully been executed, it was still possible to invoke Genesis group purchase and commit functions. The recommendation was to consider adding validation by ensuring that these functions could not be called after launch. This finding is related to the ordering issues we discussed in number 145 and 178, and also the timing issues discussed in 143 and 177 of the Security Pitfalls and Best Practices 201 module. 11 is another finding from consensus diligence audit of FATE protocol, where it was a major severity finding related to the data validation category. FATE performed some mint burn operations via Uniswap incentivized function, which calculated buy-sell incentives using overflow prone math and then minted burn from the target based on the results. Any overflows would have had unintended consequences on such minting or burning. The specific overflow probe math was because of unsafe casting from a user supplied uint256 argument in the externally visible function to int256, which is a downcast and may have overflowed without appropriate checks. The recommendation was to ensure that casts do not overflow and was addressed by the use of OpenZeppelin's safecast. This finding is related to OpenZeppelin safecast wrappers we discussed in number 177 of Solidity 201 module, dangers of integer overflow underflow that we discussed in number 19 of Security Pitfalls and Best Practices 101 module, and the broader aspect of the importance of input validation, specifically on function parameters in 138 and 146 of Security Pitfalls and Best Practices 201 module. Number 12 is another finding from consensus diligence audit of FAE protocol, where it was a medium severity finding related to the timing category, similar to number 10. Specifically, bonding curve allowed users to acquire FAE before launch, where its allocate function could be called before Genesis launch if the contract had a non-zero ether balance. So by sending even one way, anyone could bypass the checks and mint FAE. The recommendation was to prevent allocate from being allowed to be called before Genesis launch. This finding is related to the ordering issues we discussed in number 145 and 178 and the timing issues discussed in 143 and 177 of Security Pitfalls and Best Practices 201 module, and also misuse of a contract's ether balance as discussed in number 26 of Security Pitfalls and Best Practices 101 module and number 158 of Security Pitfalls and Best Practices 201 module. Number 30 is another finding from consensus diligence audit of FAE protocol, where it was a medium severity finding related to the error handling category. The issue was that its time ended function returned true even if the timer had not been initialized. Timed start time was set only when init time was called, but before that was called, is time ended function calculated remaining time using a start time of 0 and returned true even though the timer had not been started. The recommendation was for is time ended to return false or revert if time had not been initialized. This finding is related to error handling in the context of the ordering issues we discussed in number 145 and 178, and also the timing issues discussed in 143 and 177 of Security Pitfalls and Best Practices 201 module. Number 14 is another finding from consensus diligence audit of FAE protocol, where it was a medium severity finding related to the data validation category. This was specifically related to the code base using many arithmetic operations without the safe versions from safe math. The reasoning was that all values in such operations were derived from actual ETH values, so they couldn't overflow. The recommendation was that it was still safer to have those operations use safe mode arithmetic, either by using safe math or Solidity version greater than or equal to 0.8.0. We have discussed this aspect of Solidity compiler 0.8.0 and OpenZeppelin safe math in number 142, 146 and 175 of Solidity 201 module and number 19 of Security Pitfalls and Best Practices 101 module. Number 50 is another finding from consensus diligence audit of FAE protocol, where it was a medium severity finding related to error handling category. In this case, there was no checking for the return value of IVETH transfer call. It's usually good to add a require statement that checks the return value, or as discussed in number 149 of Solidity 201 module, it's safer to use something like OpenZeppelin's safe transfer wrapper unless one is absolutely sure that the given token reverts in case of a failure. So the recommendation was to consider adding a required statement or using safe transfer, which handles all possibilities of revert, Boolean and non-Boolean return values. We have discussed this aspect of correctly checking for function return values in number 142 and 175 of Security Pitfalls and Best Practices 201 module. Number 16 is another finding from Consensus Diligence Audit of FAE protocol, where it was a medium severity finding related to the timing category, similar to number 10 and number 12. In this case, Genesis Group emergency exit function remained functional after launch. Emergency exit was intended as an escape mechanism for users in the event that the Genesis launch method failed or froze. And so, emergency exit and launch functions were really intended to be mutually exclusive, but were not, because either of them remained callable after a successful call to the other, which may have resulted in edge cases in accounting. The recommendation was to ensure that launch cannot be called if emergency exit has been called, and vice versa. This finding is therefore related to the ordering issues we discussed in number 145 and 178, and the timing issues discussed in 143 and 177 of Security Pitfalls and Best Practices 201 module. Number 17 is a finding from Consensus Diligence Audit of Bit Bank Protocol, where it was a major severity finding related to error handling category. In this case, ERC20 tokens that did not return a value would fail to transfer. Recall that although the ERC20 standard suggests that a transfer should return true on success, some tokens may be non-compliant, and in such a case, the transfer call here would revert even if it were successful, because of solidity checking that the return data size matches the ERC20 interface. The recommendation was to consider using OpenZeppelin's safe ERC20 wrappers. We have specifically discussed this in number 149 of Solidity 201 module and number 24 of Security Pitfalls and Best Practices 101 module. Number 18 is a finding from Consensus Diligence Audit of Metaswap protocol, where it was a major severity finding related to reentrancy. This reentrancy vulnerability was in Metaswap swap function, where if an attacker was able to re-enter swap, they could execute their own trade using the same tokens and get all the tokens for themselves. The recommendation was to add reentrancy guard, such as the one from OpenZeppelin, where the non-reentrant modifiers are used on functions such as swap that may be vulnerable to reentrancies. We have discussed these aspects in number 157 of Solidity 201 and number 13 of Security Pitfalls and Best Practices 101 modules. 19 is another finding from Consensus Diligence Audit of Metaswap protocol, where it was a medium severity finding related to access control. A new malicious adapter could access users' tokens. For context, the purpose of the Metaswap contract was to save users gas costs when dealing with a number of different aggregators. They could approve their tokens to be spent by Metaswap, and they could then perform trades with all supported aggregators without having to reapprove anything. The risk in this design was that an existing or newly added malicious or buggy adapter would have access to all users' tokens. The recommendation was to redesign token approval architecture by making Metaswap contract the only contract that receives token approval, where it moves tokens to another spender contract, which in turn delegate calls to the appropriate adapter. In this revised model, newly added adapters wouldn't be able to access users' funds. We have discussed access control aspects in number 4 of Security Pitfalls and Best Practices 101 module, and in 148 and 149 of Security Pitfalls and Best Practices 201 module. This is also related to token handling aspect of number 159 and trust issues of 181 of Security Pitfalls and Best Practices 201 module. Number 20 is another finding from Consensus Diligence Audit of Metaswap protocol, where it was a medium severity finding related to the timing category. In this case, a malicious or compromised owner could front-run traders by updating adapters to steal from users. Because of the design of adapters where they delegate called to each other, users had to fully trust every adapter because just one malicious adapter could change the logic of all other adapters. The recommendation was to disallow modification of existing adapters, but instead add new adapters and disable the old ones. This finding is related to the transaction order dependence aspect discussed in number 21 of Security Pitfalls and Best Practices 101 module. Time delayed change of critical contract aspects in number 163, trust aspects in number 181, and constant aspects in number 184 of Security Pitfalls and Best Practices 201 module.